Greetings and welcome to Chapter 9-7, Taylor Polynomials and Approximations, Part 1. Folks, please make sure you have checked out this video. There's a link on the notes page in this particular section or for this section, and I've also put that link for you in Canvas. But please make sure you have watched this video before you move any further in this presentation. So stop this video and go watch the other one if you haven't done it. It's pivotal in understanding where we're headed over the next couple sections in this chapter. So our goal with a Taylor polynomial and approximation is to create a polynomial that is used to model a different elementary function. What we're talking about is a very basic function that that is not a polynomial. So like think the natural log of x, or e to the x, or sine of x. These are elementary functions. And our goal is to create a polynomial that can be used to model one of these functions, because if you think about it, a polynomial can have as many terms as we want and have a degree of whatever we want. So we could really create a polynomial that could come very close to another elementary function. What we'll say is the p of c, that's the polynomial function, is going to be the same as f of c, that's the elementary function. So they'll go through the same point. And p prime of c and f prime of c will be the same, meaning that they will both have the same slope at this mystery point. By meeting these two conditions, we found a first-degree polynomial approximation for a function. Now understand, it's going to be tough to find a polynomial that is exactly the same as this elementary function. But that's not the point. The point is to get something that's really close, not necessarily exact. Let me show you what I'm talking about here. So we're going to find the first-degree polynomial function p where the value and slope agree at x equals 0 for the function f of x equals e to the x. So first of all, let's see what p of x will look like. P of x, being a first-degree polynomial, will have some constant term, and then it will have a value. So it's essentially a linear equation. I am using a sub 0 and a sub 1 to denote m and b instead of using m and b for reasons when we get to bigger polynomials. And again, we're comparing that to the function f of x equals e to the x. Okay, so knowing what I know, p of 0, right? Oh, compare that to f of 0. Okay, well, f of 0 is equal to e to the 0, which is equal to 1. So I know that I want p of 0 to equal 1. Or in this case, a sub 0 plus a sub 1 times 0, that has to equal 1, which means a sub 0 equals 1. So that gives me the start of this polynomial, p of x being equal to 1 plus a sub 1 of x. All right, so now let's try to find the spot where the slope agrees. So the slope is found by looking at the first derivative. So the derivative of e to the x is e to the x. And if I'm evaluating that at the point 0, that's e to the 0, which is equal to 1. Go back over here and let's hear if p of x is equal to 1 plus a sub 1 of x. So that means p prime of x. Well, let's see here. A1 is a constant, so really my derivative is equal to a sub 1. And if I want that to agree at 0, when I plug in 0, well, there's no x value in there. So I know that a sub 1 has to equal just a plain old 1. And I got it. So at the end of this problem, my first-degree polynomial function, where the value and the slope agree at x equals 0, will be p of x equals 1 plus 1x, or just regular plain old x. Now, I know what you're saying. The line 1 plus x is nothing like the equation e to the x. But that's not really exactly the point we're going for. I just simply am looking right here. I'm looking at the point x equals 0, or c equals 0, however you want to view that. And I'm saying at that point, the value is the same and the slope is the same. So that's really neat, because just at that one spot, the slope and the tangent line, the tangent line and the equation are exactly the same for both equations. So if we would like to figure out a better polynomial to estimate e to the x, we need to go with a higher degree polynomial. So Let's find a third-degree polynomial function. And we're going to go through a very similar process to what we did in the last problem. So let's first write out our third-degree polynomial. So let's hear a sub 0 plus it would be a1 x to the first plus a sub 2 x squared plus a sub 3 x to the third power. Okay, and we're going to compare that again to my function f of x, which is equal to e to the x. All right, so let's look at the original equation. We want the original equation to go through the same value at 0. So we got e to the 0, which is equal to 1. So I know when I go over here and plug in 0 into my equation, I want the result to equal 1. So let me go ahead and plug in 0 here. Let's hear a sub 1. That turns into a 0. A sub 2 times 0 squared. A sub 3 times 0 to the third power, and I get that a sub 0 is equal to 1. Hey, that's what I got in the last problem. Okay, let's make sure the first derivatives match. So the derivative of e to the x is e to the x. So f prime of 0 is equal to e to the 0, which is 1. Let's look at what p prime of x is equal to. Let's see here. Well, that would be a sub 1 plus 2a2x plus 3a sub 3x to the second power. And when I plug in 0, I want that to equal 1. So let's see here. That's a sub 1 plus 2a2 times 0 plus 3a sub 3 0 squared. So I get that a sub 1 is also equal to 1. Okay. So now from here, I'm going to keep going. I'm going to look at the place so that the second derivatives match. So the second derivative of e to the x is e to the x. And the value of the second derivative at 0 is 1. Okay, let's see here. So let's see here. P double prime of x is equal to, well, let's see here. 2a sub 2 plus 6a sub 3 x. That's the value of the second derivative. And when I plug in 0 to that, let's see here, 2a sub 2 plus 6a sub 3 times 0, and I know I want the value of that to equal 1, I end up knowing that 2a sub 2 is equal to 1, or a sub 2 is equal to 1/2. Okay. So we want the third degree polynomial, so we gotta keep going. So let's see here, we'll look at the third derivative of e to the x, which is e to the x. And the third derivative evaluated at 0, which is e to the 0, which is 1. Okay, we'll look at the third derivative of p of x. Well, that 2a sub 2 goes away, that's a constant, and I'm just left with 6a sub 3. That's the value. When I plug in 0 into the third derivative, I get 6a sub 3, and I know I want that to equal 1, which means a sub 3 is equal to 1/6. So after going through all of that, the polynomial that estimates e to the x, the third degree polynomial that estimates e to the x, is 1 plus 1x plus 1/2 x squared plus 1/6 x to the third power. Now, if we compare the polynomial graph with e to the x, you'll see that this is a lot closer. It's a lot closer to what e to the x actually looks like with that polynomial. Really good here, not so good here, but better than just that line of 1 plus x. There's actually a nice shortcut that helps us find this Taylor polynomial. And it goes a little like this. I find that I like to see a little bit more of a pattern than what is actually shown in these definitions. So to get that across a little bit better, do you see how it's 2 factorial here? I know that this right here was all over 1 factorial. And I know that this right here would be over 0 factorial. And just remember that 0 factorial is 1. And also, like, do you see how this is x minus c to the first power? I like to make this x minus c to the 0 power. I think that that makes the pattern a little bit more clear for us to be able to see, so that you just know it's f of c times x minus c to the nth power all over n factorial, just like it is down here. And then you can just start at 0 and work your way up. I think that's just an easier way to remember this. Same thing down here for the Maclaurin polynomial definition, which, again, the only difference is that c is equal to 0 for the Maclaurin polynomial, as opposed to the Taylor polynomial, which can be at any value for c. But with the Maclaurin polynomial, you'll see that I'll write that as over 1 factorial and over 0 factorial, just so I can keep everything straight. And then I'll write that second term as x to the first power and the first term x to the 0 power. I just think that helps me to keep everything a little bit more clear when I'm going through these individual problems. Let me show you an example here on the next page. So we're just going to write the Maclaurin polynomial for f of x equals e to the x. And to do that, if we follow that definition, we know that I just have to rewrite this as e to the 0 power over 0 factorial plus, well, it would be f prime, so it would be the derivative of e to the x. So the derivative of e to the x, so that's e to the x, plugged in and then evaluated at 0 over 1 factorial times x to the first power. And then we'll have the second derivative. The second derivative of e to the x is just e to the x, so I'm going to evaluate that at 0, and I'll put that over 2 factorial times x to the second power. And then let's see here, we'll do the third derivative. Let's see here, the third derivative of e to the x is e to the x, evaluated at 0, and that's times 3 factorial, x to the third power. And then I could keep going and do the fourth derivative, the fifth derivative, but it's really nice because e to the x has such a nice derivative that I can just do that all the way out here to the nth term, which will go to the n factorial, plus x to the nth power, whatever that may be. So a very generic form. Now, I will actually go through here and simplify some things down. I know e to the 0 is equal to 1, and 0 factorial is 1, so that's just 1. And then I got 1 plus, well, that would be just x for the second term. The third term, that would be 1 over 2 factorial, which is, that's 1/2 x squared. And then I got 3 factorial. 3 factorial is 6, so I got 1 over 6 x to the third power. Hey, that's almost like it. And then we just skip out here a bunch, and we got, well, that would be 1 over n factorial x to the nth power. Very generic formula for e to the x. That works out really nice because the derivative of e to the x is e to the x, and I don't have to continue worrying about changing those top values. They were all 1. So let's take a look at the natural log function, and we're going to find p sub 0, p1, p2, p3. What this means is this just means the 0th degree all the way up to the 4th degree Taylor polynomial. So we're going to create all of those here in one shot, and we're going to use that nice shortcut formula that we just came up with. But before I do any work, I think it's really nice if you go ahead and calculate the values for natural log of x. So we're going to look at the derivatives of natural log of x all the way up to the 4th derivative, since I need the 4th degree polynomial. So that's here. The derivative of natural log of x is 1 over x, x to the negative first power, because that will actually make my life a little bit easier when I get down here to the second derivative. Right, and again, that's negative x to the negative second power. And I'll write that because the 3rd degree polynomial will be even easier, so that would be 2x to the negative 3rd power, which is 2 over x to the 3rd. And then the 4th derivative, oh, you know what, let's write it like this. The 4th derivative of f of x would be, well, I'll bring down, so that would be negative 6 x to the negative 4th power, or negative 6 over x to the 4th. And then again, we're going to evaluate it at c equals 1, which means in addition to these values for f of x, I'm also going to need to plug in 1 for each one of those. So I got the natural log of 1, which is equal to 0. I got the f prime of 1, which is 1 over 1, which is just 1, of the second derivative defined at 1. So I get negative 1 over 1 squared, which is just negative 1. I'll have the third derivative defined at 1. So that would be 2 over 1 to the 3rd power, which is 2. And I'll have the 4th derivative defined at 1, which is negative 6 over 1 to the 4th power, or just plain old negative 6. Okay. Okay, so we'll take that information and we'll start writing out our polynomials. So the p sub 0 of x, that 0th degree polynomial, well, that's just going to be based upon that equation, that Taylor polynomial equation that I came up with. I know it's just going to be f of c. So in this particular case, that's f of 1, which according to everything that it did is just plain old 0. So that's actually the 0th degree polynomial there. I don't like saying 0th degree polynomial. What about the 1st degree polynomial? Well, according to my equation, that would be f of 1 plus f prime of 1 times x minus c, so x minus 1. What is that actually simplified down to? That gives me 0 plus, let's hear, f prime of 1 from the previous page is 1 times x minus 1. So I simply end up with x minus 1 as being the answer here. X minus 1. Okay. What about the 2nd degree polynomial? And according to my formula, it will be f of 1. Again, I like to write that, right? So that's times x sub 0 to the 0 factorial, right? Because it's the first term, the 0th one. And then if I do the first, it's the first derivative at 1 times x minus 1 to the 1st power all over 1 factorial. And since I want to go out to 2, I just do it again. So it's the 2nd derivative at 1 times x minus 1 to the 2nd power over 2 factorial. Okay, and when I start plugging in the numbers here, let's hear. I actually already did this part, right? That part right there is the x minus 1 from the previous problem. So really all I got to do is add on this ending part. And what is that? So the 2nd derivative was that negative 1 over 2 factorial. So I get negative 1/2 times x minus 1 to the 2nd power. So that's I can consolidate terms and everything like that and just write it as x minus 1 minus 1/2 times x minus 1 to the 2nd power. The 3rd degree polynomial. What about the 3rd degree polynomial? Okay, so again, if I do that and I just fill it in here, that's the first term. Here's the 2nd term for 1 factorial plus the 2nd term. This is all the way out there to x sub 2, right? We got the 3rd derivative all the way out of here. Okay, x minus 1 to the 3rd power over 3 factorial. And again, if I'm doing this already, I've actually already did this with the last step. So that's that x minus 1 minus 1/2 x minus 1 squared. I've already done that part. So now just the new stuff. So let's hear. The 3rd derivative at 1 was equal to 2. So I got 2 over 3 factorial, so it's 2 over 6, and then times x minus 1 to the 3rd power, or if I simply write that down a little bit better, let me do the math there, I get plus 1/3 x minus 1 to the 3rd power. And we have just one more to go, so let's hear the 4th degree polynomial. Let's hear, so we'll just write out all that junk we had before, 0 factorial. Plus, that would be x minus 1 to the 1st over 1 factorial plus f double prime, I forgot my derivative there, f double prime of 1, x minus 1 to the 2nd power over 2 factorial, triple prime, x minus 1 to the 3rd over 3 factorial, and then we just got to do the 4th derivative of 1. Of x minus 1 to the 4th power over 4 factorial. Okay, let's see here. Which equals, again, we've done this already. That's that stuff from the previous step. Right? Okay, and then we just got to do the new stuff. So let's see here. Plus, the 4th derivative was defined as that was negative 6. So we got negative 6 over 4 factorial. And 4 factorial, let's see here, 4 times 3 is 12, times 2 is 24, times 1, of course, is 24. And then we got x minus 1 to the 4th power. Simplify it all down. X minus 1 minus 1/2 x minus 1 to the 2nd plus 1/3 x minus 1 to the third minus 1/4 x minus 1 to the fourth power. Whew! That was a tricky one. Zoom out and take a look at all that nice math work we just did. Wow. Cool. And here's a graph of the natural log of x, which is the red curve, and the blue curve, which is that fourth degree polynomial we came up with. Now I want you to notice we have made that value at 1 be the same. So right there is x equals 1. And you'll see it's pretty good. It's pretty good right here. It does fall off, right? It's not perfect. It's not perfect. But at the value of 1, very close to being exactly natural log of x, and actually very good at being the natural log of x. We could almost use a Taylor polynomial to estimate a value for a curve. And that's what we're going to do here with the next problem. We're going to find the third degree Taylor polynomial for f of x equals sine of x at x equals pi over 6 and use this to approximate the sine of 0.5. Okay, so here's what I want you to do right now. I want you to pause the video, and I'd like you to just find the third degree Taylor polynomial for sine of x at x equals pi over 6. Don't do the approximation yet. Just hang out and wait. I want you to actually evaluate or find the third degree polynomial first. So go ahead, pause the video, find that, and then I want you to check yourself with what I'm going to show you here in a second. No, really, I mean it. Pause the video right now and find this polynomial. I'll be here when you get back. Promise. Okay, so you'll see what I did up here in the red is I went ahead and did all of the derivatives, the first to the third derivative of sine of x, and then I plugged in the value pi over 6 into those respective equations. Then I came up with the Taylor polynomial. I followed my pattern, and I came up with the third degree polynomial being 1/2 plus the square root of 3 over 2 x minus pi over 6 to the first power minus 1/4 x minus pi over 6 to the second power minus the square root of 3 over 12 x minus pi over 6 to the third power. Now, if I want to actually evaluate and approximate the value of sine of pi over sine of 1/2, I can just plug that right into my polynomial function. Now, I would recommend using a calculator for this because it does get a little tricky, but when you do that with the values, you end up with 0.47942555322. Now, compare that to the actual value of 0.5. So the sine of 0.5. Check this out. 0.47942555386. Holy moly. This polynomial is good enough out to that many decimal places. Check it out. Check it out. That is amazing that we can use a polynomial to guess at the value of the sine of 1/2 without actually having to look at the actual sine of 1/2. That's what makes Taylor polynomials and Maclaurin polynomials so cool. We can use them to estimate values for these elementary type functions that are not polynomials. So here's a couple homework problems for you guys to complete. Not too difficult of an assignment, but you have to be very meticulous with this and you'll get used to the pattern that you see. So good luck with your homework, guys. If you have any questions, you know where to find me. Have a good day. See ya!